Hey there, welcome back to the channel. So today in this video lecture we'll be solving this problem is graph bipartite. So we're given an undirected graph with n nodes where each node is numbered between 0 and n minus 1, and the graph is stored in the adjacency list basically, and we do not have any self edges. There are no parallel edges between the nodes. Now if v is in graph u, then u is in graph v, means the edges are bidirectional. The graph is undirected, right? The graph may not be connected, meaning there may be multiple connected components of the graph, right? So what is the definition of a bipartite graph? A graph is bipartite if the nodes can be partitioned into two independent sets A and B such that every edge in the graph connects a node in set A and a node in set B, right? So what does that mean? So we can, if the graph is bipartite, if we can partition the graph into two independent sets, A and B are independent sets, such that every edge in the graph connects a node in set A and a node in set B. Fine. So let's take an example to understand it better. So we'll return true if only the graph is bipartite. Otherwise, we'll return false. So let's take an example to understand better. So let's take this example. So let's ask ourselves whether the graph is bipartite or not. So can we divide the graph into two independent sets such that there is an edge between, every edge in the graph connects a node in set A and a node in set B. So something like the edges must be like the edge must have endpoints in both of the sets. Fine. So is it possible for this graph? No, there is no way to partition the nodes into two independent sets such that every edge connects a node in one and a node in the other. So let's see how and why. So let's take this example which we were studying. So the example is we have 0, then we have 1, then we have 3, then we have 4, and here we have, the graph is something like this. So what we can do here? So let's start with this. So let's say we partition the nodes into two sets. Let's take set A and set B. Now every edge must connect the nodes, and one of the nodes must be in set A and another node must be in set B. So let's take the two sets A and B. Let's try to put the nodes into these two sets following the condition that we are given for the bipartite graph. So can we put 0 here and 1 here because there is an edge between 0 and 1? Yes, we can. So can we put 0? Can we put 4 here? No, because we have an edge between 0 and 4. Can we put 4 here? No, we cannot because we have an edge between 1 and 4. So there is a problem. We can't separate the nodes into two sets such that every edge connects two nodes where one of the node is in set A and another node is in set B. We'll always find a pair of nodes in the same set which has an edge. So in this case we'll return false. The answer for this is false. So let's take the next example, 0, 1, 3, 2, 0, 1, 2, 3. So 0, 1, 2, 3, so like this. Okay, A and then we have B. So let's put 0 here. Can I put 1, 3 in the same set? We cannot. I cannot put 1 and 3 in the same set A. So I have to put 1 in the other set. I have to put 3 in the set B. Can I put 2 in the set A? Yes. Is it a valid combination? Yes. Because we do not have any edge between 0 and 2. We do not have any edge between 1 and 3. So in this case, we'll return true. So how we can solve this problem? Just think about it. Having an edge between two nodes, where one of the nodes lie in A, another node lies in B, and not having an edge in the same set between any pair of nodes, that's the ideal condition we want for the graph. How can we confirm that our graph follows that condition or not? The trick to solve this problem is basically somehow coloring the graph. Why? Because let's take this example. Now these two nodes, node number 0 and node number 2, can be colored in one color, let's say black. So they are colored black. And these two nodes, node number 1 and node number 3, they are colored in red. Right? Now we have two colors of nodes in the given graph. The edge can only be present between the nodes of different colors. So between black and red only. We can always have an edge like this. And that will give us our solution to this problem. Basically, try to color the nodes such that no two nodes which has the edge between them possesses the same color. Right? So let's see how we can do that. Let's take the same example which was valid, this one. Let's color the nodes into two different colors. So let's start from node number 0. Let's color it like this. Let's color it blue. Now, since I have colored node number 0 to be blue, the color of the nodes which are adjacent to this node, which are connected by an edge to this node 0, must be colored differently. Let's do it. Let's color node number 1 black. Let's color node number 3 black. Now, let's move to node number 2. Does node number 2 follows the conditions? Does it satisfies the condition? Yes, because here we had node number 0 and it is colored blue. So we do not have any trouble with this edge. Do we have any trouble with this edge? Not yet. If we color node number 2 to be blue. So I color node number 2 to be blue, because then I'll have no trouble having this edge in my graph. Fine. Now let's move more deep to node number 2. Do I have any trouble for node number 2 for having the edges with node number 1 and with node number 3? The answer is no, because both of these edges are valid. We have opposite colored nodes at the end of these edges. At the end of this edge, we have opposite color nodes at the end of this edge as well. So so in this fashion, I have colored node number 0, node number 1, node number 2. Now let's move more deep to node number 3. Do we have any problem with this node 3 because of the edges which connects to node number 0 and which connects to node number 2? And the answer is no, because we have opposite colored nodes for both of these edges. Fine. So this graph is fine. All we have to do is to traverse every node of the graph and just confirm whether we can make the edges, whether we can make the adjacent nodes for that node to be of entirely opposite color, to be of entirely different color than the color which the current node has. That's what we have to check for the graph which we are given. If it is possible for every node of the graph, then what we're going to do is we'll return true, otherwise we'll return false. Fine. So that's the thing, that's the approach. Let's try to do the same for this node. Let's try to do the same for this graph. Start from node number 0, color it blue. Move to the adjacent nodes. So let's move to node number 1. I have to color it like this. I have to color it red. Let's move to node number 4. The color of the node number 4 must not be blue. It must not be red. Why? Because both of these nodes are connected to node number 4. I can't color node number 4 to be blue. I can't color node number 4 to be red, That means I can't put node number 4 into the set of blue nodes. I can't put node number 4 into the set of red nodes. So where to put node number 4? Node number 4 do not have any place to stay, right? That means we can't build those ideal sets which we are trying to build for the graph. And so we return false right from here. Fine. Let's jump to the next step and let's think about how we can implement the strategy. Now we can see that as we found a valid graph here, what we did is we just moved deep down in the graph. We started from some node 0. I moved deep down to node number 1, then node number 2, finally to node number 3, and so on. Fine. 0 to 1, 1 to 2, 2 to 3, right, like this, and kept on coloring the nodes while satisfying the conditions that we have. That is, both of the ends of the nodes are colored opposite. Fine. So let's just see how we can implement the solution, how we can use the depth first search strategy to solve this problem, right? So let's just think about it. Let's build the solution right here, and then we'll go to the implementation part. So let's take this graph, this very graph which we had, the valid graph, 0, then I have 1, then I have 2, then I have 3. So I have things like this. Okay, now let's start a DFS search. Let's start a DFS function which starts from node number 0. So what does this DFS function return? DFS node returns whether we can color the node, whether we can color the given node and its child node in the opposite colors or not. So let's start from node number 0. Now from node number, and we also take an array, right? We take an array here, and 0, 1, 2, and 3. So let's call it a color array. So let's start from node number 0, DFS 0. Let's color it to be red. So let's put 1 here for that. Red is 1. So let's move to the adjacent node, which is node number 1. So let's see. So this is call stack, right? This is my call stack, inverted call stack. Then we have DFS 1, right? DFS 1, and I visit this node. While I'm moving from node number 0 to node number 1, where node number 1 is the child node for node number 0, I'm also turning the color, right? The color was 1, now the color becomes 0. That means while I'm calling this function, I need one more thing here, that is color as well. So initially the color was 1, now the color becomes 0. So I pass the color, I turn the color. So let's color node number 1 with the color of 0. So let's put 0 here. Now let's move to the next function call for the next node at the next depth, which is node number 2, and the color for this node is again 1. So let's put 1 here. So what is 1? 1 represents the red color. So let's put 1 here. Move to the next depth, which is node number 3, right? Okay, now while traversing the adjacent nodes of node number 2, I find node number 1, I find node number 3. I find that node number 1 is already visited and has opposite color than what the node 2 has, while node number 3 is unvisited and it has no color. So let's call this function DFS for that node, for node number 3, and the color would be 0, right? We turn the color. So now here we can see that for 3 we'll put 0. Okay, so it's black, so we put 0. Now for node number 3, I can see that both of the nodes are visited. Node number 0 is visited, node number 2 is visited, and they satisfied the conditions. Node number 0 has color 1, node number 2 has color 1, while node number 3 has color 0. So these nodes has opposite set of colors. That means I'm going to return true from here, right? Why I'm returning true from here? Because node number 3, I'm good with node number 3. It has like, it follows the bipartite graph properties. The adjacent nodes are colored. Now I come back to node number 2 and I'm returning true from here. So I'm receiving true here, right? So at node number 2 I'm receiving true. So I will return true. I will return true at the for the calling function here. So this will again in return true to the calling function. So finally I'll have true as my answer, because it is possible to color the nodes in like, or it is possible to divide the graph into two independent sets such that there is an edge, and the edge has endpoints, one of the endpoints in one set and another endpoint on the another set, which was our condition that we had in the problem statement. Now, why this will not work for some graphs? Let's also see that as well. So let's take a non-ideal graph, or the graph which we had here, 0, 1, 2, 3, this thing. So we have this 0, 0, 1, 2, 3. So the thing is like this, and we have an edge here. So let's start the DFS for this. Let's create an array. The array is something like this: 0, 1, 2, 3. And let's take this call stack here, and let's see what we can do. So let's first call the function DFS for node number 0. Let's color it red. So for node number 0, let's color it red. Let's put 0 here. From node number 0, so this is traversed. Let's move to node number 1. Traverse this, call the DFS function for this for node number 1, and turn the color to be 1. Color this with like black. Okay, so this is black. Let's move to the adjacent node, another adjacent node, which is node number 2. We are moving deep, and let's call this DFS function for node number 2, and the color that we want for node number 2 is 0, or the red color. So for 2, let's put red color. So it is 0. Let's call the function for the next node, which is here, node number 3, DFS 3, and this is, or let's say, let's call this function, okay, let's just do it 3, and then let's turn it to be black. So let's color it to be black. So here we have black color. Now notice that I'm also traversing this node. This node, which is node number 0, is also the adjacent node. Remember, we colored node number 2 with the red color, and we can see that node number 0 also has the red color, and both of these nodes are adjacent. They are adjacent nodes. That means this edge is an invalid edge. This is not possible. We can't put the node number 0 and node number 2 in two different sets. Fine, because they have the same color. So we return false right from here. So for, let's say, DFS, we'll have something DFS, let's say 2, and for color for node number 2 is red, which is 0. So we'll return false from here. False, false, false. Finally, the answer will be false. So this is a non-ideal situation when the graph is not bipartite. I hope you got how we'll check whether the graph is bipartite or not. Let's jump to the code implementation part. So here's the problem. It is available on the lead code. The name of the problem is Graph Bipartite 785. So let's see how we can code it. So let's first find the size of the graph. So graph size is graph.size, and let's create a visited array. Let's create a visited array visited of size n, initialize it with -1. Let's iterate over all of the nodes from 0 to n minus 1. And if some node is unvisited, visited I is equals to -1. In that case, let's recursively, let's just see, let's take a Boolean variable, let's call it check, and let's call the function, let's create an helper function here, or let's say DFS function, which takes in the node, the parent, okay, and then we'll have, let's say, the visited array, or let's call it color array. Let's not call it visited array, let's call it a color array, right? Or let's just stick to the visited definition, and let's say we are passing a color here. We pass a color here. So visited array, then let's pass the graph that we have. Okay, so let's pass this graph here. Fine. Now, so this is color, COLOR, visited for this node. Let's store this color for this node. Iterate over the neighbor nodes, or let's say child nodes, for this graph. So if this child is not visited, is equals to -1. What we're going to do in that case? So we'll basically pass this child node, and then we'll basically turn the color to the other one, and then we'll pass the visited array, then we'll pass the graph. So if this check is false, then we'll return false. Fine. Why will return false? Means this child is unvisited. The child is unvisited. We're gonna call DFS recursively for that child, and if that child returns false, means the graph is not bipartite, so we return false right from there. Otherwise, if this child is visited, then let's check if the color for this child and for its parent is same. The parent is this node. If it is the case, if the color is same, then return false. Fine. Otherwise, at the end, you're gonna return true. If both of these conditions are not met, then we'll return true by default. So let's call this function DFS for every visitor. So why we are using this for loop? What is the purpose behind using this for loop? Because we may have a graph like this. We may have a graph, a disconnected graph. Okay. So let's think about it. Why we were like using that loop. So we have graph. We may have a graph like this: 0, 1. Then we have 2. Something like this, 4, 5. So we can check this is not bipartite, this is bipartite. Now we also have to check whether this is bipartite or not. But we can see that if I run a DFS from this node, this will only traverse this component. I need to run the DFS for this component as well, or for other disconnected component which this graph may have, like this, some other component like this. I also have to run DFS separately for this, DFS separately for this, DFS separately for this, and so on, so that I get that actual answer array prepared for the entire graph, right? So that's why I'm using that for loop. Whenever I find an unvisited node, I'm going to call this DFS function for that node. So pass in this node I, and the color for this node is 0, pass the visited array, pass the graph, and this check will have my answer here. Let's return this check. So if this check is false, we're going to return true. Okay. If this check is false, then we'll return false. Otherwise at the end will return true. Okay, so that's the thing. Let's submit it. Okay, got accepted. Now we can see that the time complexity is not a big deal because this is just in DFS, and we know the time complexity for DFS is big of n plus e. Why e? Because we may have graphs where the edges matter more than the number of nodes, right? Like e is way higher than the number of nodes. That's why it is e plus n. While the space complexity is again constant because we're not using, it's not constant, we are using that color array, so it's big of n, while we also consume a stack space of big of n because of the call stack which is used while storing to store those DFS calls. Okay, so that's all for this video. I hope you enjoyed the video and you learned something from this video, and I will see you soon in my next video, and stay tuned with me, stay tuned in other series as well, and we'll see you soon in my next video.